Point 7, we're going to work with some function notation, combinations of functions, etc. And we're going to start with a little bit of algebra of functions. So let me show you some of the notation that we're going to use. Let's see, algebra of functions right here. Over a little bit. Perfect. Stay. Good boy. So f plus g of x, f and g are functions, and we can write the combination or the addition, subtraction, multiplication, and division of functions in a lot of different ways. You can just write it like this without all the trappings of the of x, or you can write it in a fancier notation, f plus g of x, and it means the same thing as f of x plus g of x. So there's 1, 2, 3 different ways to write f plus g of x. And, I'll go back and forth between all of these, depending on what's convenient. But in a similar way, you can subtract functions, you can multiply functions, and you can divide functions. The one thing I want to caution you about is this fg is f times g, not to be confused with what we're going to do later in the section, which would be function composition f of g. So let's see. We'll start out with kind of a nice basic problem to practice some of these things, and that would be problem number 12. You guys are going to get vertigo watching this thing. All right, so problem number 12. F of x is x squared plus 2x. And g of x is x squared minus 3x. So let's... Oh, you know what? I grabbed the wrong g of x. Yep, I grabbed g of x from problem number 11. I don't know. This looks pretty fun. So we'll call this problem 12-ish. There you go. And we'll still do the same motions for problem 12-ish that we would have done with problem number 12. And that is we want to find f plus g, f minus g, f times g, and f divided by g. And really, like I said, this is only practice with the notation. So f plus g, the first one would be x squared plus 2x plus x squared minus 3x. And basically what that's going to ask you to do is add up the like terms. So I'll get 2x squared minus x for x, f of x plus g of x. F plus g of x will be another notation for that. Likewise with f minus g. The only thing with f minus g is that you got to be a little bit careful distributing the negative sign. X squared plus 2x minus x squared minus 3x. So if you distribute that negative sign, I get x squared plus 2x minus x squared plus 3x. My x squareds cancel. My x's add. I get 5x as f minus g of x. Continuing with f times g of x, that's going to be x squared plus 2x times x squared minus 3x. What operation are we going to have to do in working with this one? Yeah, FOIL. X to the fourth. All right, plus 2x cubed. And then the last term. Nice. And you've got like terms that you can combine here in the middle. So we get x to the fourth minus x cubed minus 6x squared as f times g of x. So, okay. Not bad so far. The last one is actually kind of easy, but there is a little bit of a subtlety or nuance that I'm going to discuss with f divided by g. F divided by g is simply x squared plus 2x divided by x squared minus 3x. Now, one thing that I've ignored throughout this problem is that they, in addition to asking you to define these things, they also want the domain. So let's pause for a second with this last one, because the domain for the previous three of these is just going to be negative infinity to infinity. They're just polynomial functions. There's no place where you can have a 0 in the denominator or a negative underneath the square root. But here, you can have one of those. In fact, where? All right, when x equals 3, where else? Where else can the denominator equal 0? Yeah, when x equals 0. So our domain is everything but those. So it's x not equal to 0 or 3. Now you might see it in the book written a little bit more fancy, and that would be the set of x such that x is not equal to 0 or 3. So you might see it written like that. The big part that I want to see is that x can't equal 0 or 3. So that'd be your domain. Okay, so that's problem number 12. Kind of a little intro into some of this notation. Let's continue with domain and range. Well, actually just the domain part. And that is, let's look at problem number 18. So again, you're focusing on what values of x you can put into your function. So the domain is f equals the square root of x plus 4 minus square root of 1 minus x over 4. No, pardon me, over x. Over x. There we go. I should probably write that as f of x. So there's a lot of things that can go wrong with this function. This problem can have a lot of issues in terms of putting in values of x. So what do you see? What catches your attention? All right, so we can't have x equals 0. Can't be a negative underneath the radical. So that really gives us two things we have to worry about, right? Because we have two radicals. We have to have, the first part, we have to have x plus 4 is greater than or equal to 0, meaning x is greater than or equal to 4. And for the second one, I want 1 minus x to be greater than or equal to 0. How do you want to solve that one? Negative 4 here. How do you want to solve this one? For me, the easiest thing to do would be to add x to both sides. So 1 is greater than or equal to x. Now I need all these things to be happening at the same time. I need the intersection of these sets. So let's see where that happens. So let's take a look at x is greater than or equal to negative 4. So that's here. So x is greater than or equal to negative 4. Is this one. And I want 1 is greater than x. Maybe it's more convenient if I write this in a different way. X is less than or equal to 1. So that would be here, a 1. And I want everything to the left of 1. Let's see if I got a better one than that. There we go. So I want everything to the left of 1. That's going to be this direction. And I'm going to have to throw out 0. But what I need out of this is I need to find out where these things overlap. So how would you describe where they overlap? Right. Between -4 and 1, excluding 0. So you could write it like this. You could write -4 to 0, union 0 to 1. Or you could write it with inequalities. You could write it as -4 is less than or equal to x is less than 0, union 0 is less than x less than or equal to 1. So there'd be a different way to write it. But what I want you to see is that the domain is where these things overlap, where we're not going to have any problems with your function. If you're looking at this on a graph, then what you should see is that the function is only plotted for those particular values of x that we found to be in our domain. So y equals the square root of x plus 4 minus square root of 1 minus x divided by x. Let's turn that on. Okay, and the function seems to be showing us what we saw, that it's not defined at 0, and it goes up to 1 and down to 4, down to -4. So kind of an interesting looking function, but its domain visually matches what we calculated, is what you should be seeing. All right, that was a lot of discussion on problem number 18 here. So let me pause and see if there's something else you'd like me to add, something that might have not been quite clear. Looking okay on 18? Okay, let's keep going then. Let's take a look at problem number 24. We're going to start doing something called function composition right after we do a function addition. So problem 24 gives us two functions. F of x is x squared, g of x is square root of x. It says draw the graph on a common screen to illustrate graphical addition. So I think I'll do that up here. What we're going to do is graph two graphs. You know what, maybe we can do this on our graphing calculator if you want to learn something new here. Now what do you know about the domain of g of x? Before I even graph this thing, what can you tell me about the domain of g of x? Can't be negative. So when I set up my window, I'm going to set it up for x greater than or equal to 0, or maybe just a little bit to the left of the x-axis, or y-axis, I should say. So here are my two functions, x squared and the square root of x. Let's put those on our graph, and we'll graph, say, from, well, currently I've got a window from -4 to 4, and from 0 to 16. Let's just use that one. Like, it's quite likely your calculator is set up with the same graph. So here's your parabola, followed by the square root function. Now when I add these two together and graph square root of x squared plus the square root of x, it's simply going to be addition of points. You're going to be adding the y coordinates from each of these two functions to get the new function. Well, let's zoom in a little bit on this graph to get a better look and appreciation for what's going on here. So One good way to zoom into your graph is with a feature called Zoom Box. Does everyone have a screen that looks kind of like what I have here? Press the Zoom key, and then the first option there is Zoom Box. And what this is going to do is it's going to create your new viewing window. It's going to put a cursor in the middle of your screen, trace around a little bit. I'm going to bring this down to about 3 or so. And when you press the Enter key and then start dragging around, what you're doing is you're choosing your new viewing window. So I'm just going to make a tighter viewing window for my graph. I want to go all the way down to y equals 0. And I've got a new viewing window. When you press Enter, it'll just change things up. And what happens when you're graphing f of x plus g of x, really you're just adding coordinates. So for instance, at x equal 1, both of these functions are at a height of 1. So 1 for the square root of 1, 1 for 1 squared. Well, if I add these two together, 1 plus 1 should give me 2. If I go to my other function, I'm there at a height of 2. And that's really all they're asking you to do for problem number 24 is realize and understand that when you add those two together, you're just adding the y coordinates. Let's move on to function composition. Function composition is what we do to kind of create new functions. You're combining them. You're adding them to adding is not exactly the right word. But the notation for function composition looks like this. And I want to look at it in the book first because their little composition symbol is much better than mine. Earlier I said I want you to be careful that you don't get confused between the times and the function composition symbol. This is the function composition symbol. Another way to write this, f of g of x, is like this, f of g of x. You're putting g into the function for f. So you're putting these two things together. We can do that in a couple different ways, depending on what's being asked of us. We'll start with problem number 28. Probably just 28a, but let me just take a look back here. So for the next few problems, f of x is going to be this function, 2x minus 3. F of x is 2x minus 3. And g of x is 4 minus x squared. So problem 28a asks you to find f of 2. Well, when you're working with these things, let's work from the inside towards the outside. So we'll start with f of 2. Can anyone tell me what f of 2 is going to equal? Yeah, 1. 2 times 2 minus 3 is 1. So f of 2 is 1. So equivalently, this is f of 1. What's f of 1 give us? Yeah, negative 1. So f of 2 is negative 1. I guess we'll do part B as well. So this is part A. Part B is g of 3. So this time we need to work with our other function and see what we can come up with when we do g of 3. So I'll give you a chance to work on this one. As with the last one, let's start with g of 3. Start with the inside. Olivia, what'd you get for g of 3, please? Good. 4 minus 9 is negative 5. And so that's g of negative 5. That didn't show up very good. Negative 5. What was g of negative 5 then? Good. Negative 21. Now this idea of substituting into a function and then substituting again is not limited to just numbers. You can do that with functions themselves. So let's try some function composition work. For instance, problem number 31b and 32a. So 31b asks you to find g of f of x. Now the book writes it like this, and you might see me write it like that on a test too, but I think for practical purposes it's probably better understood like this: g of f of x. Like that. At least that's the way I like to explain it. Now, to calculate this, well, let's start with what we know. We know what f of x is. F of x is 2x minus 3. That's from the function that they gave us at the start of the problem. So that's something that's going to be given to you. You're not going to have to know that off of, out of the ether or something like that. So there's our input into g. Now let's look at the rule for g. The rule for g, and let me just write it up here, g of x was 4 minus x squared. So what I have to do is I have to take 4 minus this thing squared. 4 minus 2x minus 3. Let's see if I can make that a little darker. 2x minus 3, like that. So the first thing we have to do is we have to square this out. It's helpful if you can square that out in your head, but don't square it out by squaring this and then squaring that. If you need to, there's nothing wrong with it. Go off to the side and write, say, 2x minus 3 times 2x minus 3. 2x minus 3 times 2x minus 3 gives you 4x squared minus 6x plus 9. And when you combine like terms, 4x squared minus 12x plus 9. The last part of this will be to distribute the negative and then collect like terms. So 4 minus 4x squared plus 12x minus 9. And the like terms you can combine are the constants. And actually, I probably should have written it in descending order of the exponent. Minus 4x squared plus 12x minus 5. If you wrote it like this, I'm not going to complain unless I give you instructions in the problem to write it in descending order. We'll see soon enough in Chapter 3 that it's handy to write these things in descending order of the exponent because this leading coefficient tells us a lot about the graph of this polynomial. Let's try problem number 32a. So still sticking with our same functions. 32a. F of x is 2 minus 3 or 2x minus 3. In 32a, they asked us to find f of x. F of x. So this one's kind of strange. This process where you take and put the value of a function back into itself is called iteration. So you'll see this kind of process a lot when you do things like population growth, if the population is growing by 3% a year, you're going to keep on putting things back into the function of 1.03 to the x, or 1.03 times x. In any case, f of x, start with what's in the parentheses. That's f of x. So f of 2x minus 3. Thank you. That term then gets plugged back into f of x itself. So 2 times 2x minus 3, and then we still have the minus 3 on the outside. So 4x minus 6 minus 3, or better yet, 4x minus 9 for that iteration. Why don't you try problem number... we'll do these together. Let's do two problems together based on the graph in the book. Problems 34 and 36. And I guess the nice thing is that there's really not a whole lot of calculation involved. Let's start with problem number 34. They ask us for g of f of 0. So where are we going to start? Well, start on the inside. What's f of 0 equal? 0. So if I have g of f of 0, that's the same thing as g of 0. What's g of 0? 3. It's just the y coordinate there. So 3. So that's problem number 34. Basically just looking at the graph. Why don't you try problem number 36? It might be helpful to write 36 as f of g of 0, and then work it the same way we did 34. Work from the inside out. Start with g of 0. Once you find g of 0, then find f of whatever point. Okay, so let's start with the inside part first. What's g of 0 equal? 3. So g of 0 equals 3. And then if I put that in, it means I need to find f of 3. F of 3, 1, 2, 3. What's it look like f of 3 is? 0. Somebody got 4.5. Are we okay with this one? Okay with that conclusion? I don't know. I kind of like that problem because it's just short and sweet. It's not a problem that I would use to try and trick you. It's just, do you understand the relationship between these x's and that function composition? So it's a problem that I'd put on the test thinking, okay, let me give them an easy one. But if there's something that isn't clear about that, let me know. All right, sure. Appreciate the question. Let's start with g of 0. That's the inside part of this. So you're going to look at the graph for g, add x equals 0. So here's the graph for g, here's x equals 0, and add x equals 0, you get g of 0 is 3. That's the y coordinate when x equals 0. All right? So this g of 0 is interchangeable with 3. So I'll put a 3 in here for g of 0. Now I want to look at the graph for f. The input for f is the value of x equals 3. So let's find x equals 3. 1, 2, 3. And for x equals 3, f of x is 0. It's right on the x-axis. So that's where we get the 0 there from. All right, thanks for the question. Let's do the same thing with problem number 40. G of f of 2. So they give you a table of values here, and they ask you to work with the table. So, Zareen, where should we start out with for problem number 40? What should we look at first? Say again? All right, so let's start out inside the G. Let's start out with f of 2. What's f of 2 equal? So f of 2 is 3. So f of 2 is 3. So equivalently, that's g of 3. And what's g of 3? G of 3 is 6. So again, kind of a quick problem there for us. Same kind of thing though. Figuring out based on the input what the output is for f. The output was 3. 3 becomes the input for g. The output is 6. G of 3 is 6. Let's take a look at problem number 52. Yeah, Michael? Yeah, yeah. That's kind of funny because those two are just different notations for the same thing. Yeah, nice observation. Yeah, it's kind of amusing that the author did that. I'm not sure they realized it though. Problem 52. F of x is a square root of, or f of x is x squared. G of x is the square root of x minus 3. Let's put those two functions together in various ways. So let me write them down for us again. F of x is x squared. G of x is a square root of x minus 3. And they ask you for a lot of things here. So probably only do one of these type of problems. But let's start with f composed with g. F composed with g might be better written as f of g of x. And let's start with the outside function. I hope that doesn't mean I lost my sound on this. So let's start with the outside function. Start with the inside function. G of x is the square root of x minus 3. And let's put that into our function for f. That would look like this. The function for f says square whatever you put in here. I'm going to square the square root of x minus 3. What happens when I square that square root? Just x minus 3. And one of the things they ask us for, and this would be the domain, and I'm going to assume that it's the domain of the resulting functions. So in this case, the domain of that function would be all real numbers. It's just everything. So the domain would be negative infinity to infinity. It's just a polynomial. What if I did things the other way? G of f says g of f of x. This time the inside function is which one? It's your x squared. So g of x squared, so g of x squared, so you're going to take x squared and plug it into the function for g. Square root of x squared minus 3. Now the domain of this one is a little bit more of a problem. It's a little bit of a pain, in part because 3 is not a nice perfect square. But what we have to have true about this, x squared minus 3 is greater than or equal to 0, is, well, this has to be always greater than or equal to 0. I guess one way I could do this, I don't want to explain this really easily. I need to know where this equals 0. X squared minus 3 equals 0 when x squared equals 3 or x equals plus or minus the square root of 3. You can test points in this. This is only going to be positive in the outside intervals. So there's a big chunk missing from the domain here. You're going to have this gap. If you were to graph this function, there'd be a gap between negative root 3 and root 3. So that would be your domain. Domain is this stuff right here. So from negative infinity to negative square root of 3, bracket, union, square root of 3 to infinity. Tell you what, I'm going to break this up into 2 parts so that I can give you a break here. It's starting to go a little bit longer than I anticipated, so let's take a break here. I'll see you in about 8 minutes.